Okay. Better. And Harsha is not that, but he can attend the recording, right? Testing. Okay. How did the homework go, or how is it going?
Yeah, it went well. I was able to turn it in last night or this morning.
Okay.
Yeah, the interpretation parts,
Uh-huh.
I guess were a little difficult.
Did you figure it out, or?
I mean, kind of just breaking up the Lagrangian and the partial derivatives with respect to, and then describing what that means. I just don't think I know. I understand it 100% as well.
Yeah, maybe you're expecting that, or maybe you're over expecting the questions gauge. But ask me again. I think I'm going to do similar examples.
Okay.
Today. In fact, I was thinking I will also try to do the example you brought it up last time. I think it's a good thing to do. It might even be interesting to do it in the small angle approximation that we're going to do later. So
Okay.
I plan to do that, or at least plan to construct a problem associated with that. We'll see. So keep the question, but do ask me whenever the context comes. So it might be useful.
Okay.
Just address them. Oh, so first the homework, right? So I have not posted the new homework. The new homework will be on small angle approximation. And I'm not sure if I would be making it due on 18th. It might be, but tentatively it is March 18th. So this is tentative. I think I'm running a little behind, so I might postpone it to the next Tuesday. But on Tuesday, I'll tell you the status is. So this is not uploaded yet, but the questions are ready. And this is April 6th. This is in class and now Zoom. Right? Okay. So let's do a couple of problems related to pendulum itself. And there's this interesting problem actually. The question is you have this stick, and often you try to balance this, right, like this. And often you have to look at it, and then the way it is falling, you try to balance it. But now the question is, the video doesn't show. That's going to be difficult. But I'll draw a diagram, so hopefully it will come on. Now the point is, the question you can ask is, now you don't get the feedback, right? And you only oscillate it like this, right? And the question is, can it be balanced? Is there a certain frequency, or is there a possible mechanism of this? Suppose you control this function. If you do this oscillation in the right way, can you actually balance it or not? And this will be called an inverted pendulum. And this is called an inverted pendulum. And let's see what whether it is possible to do that or not. So this is inverted pendulum. And we won't completely try to answer the problem. So the question, right? I think since on the video this did not come out, if you have a pendulum have the angle theta here. And gravity is downward. Right. And if you move this point, first let's say, as of now, what we will do is we will move this. So let's say this is a point, so this is point X, comma Y. Right. And let's say this point is, what should I call this? X naught, Y naught. And what I'm saying is that if you're given X naught as a function of time, is there a particular functional form that you can give which will actually stabilize this and won't let it fall? Okay. And yeah, so that will be called inverted pendulum. Now let's try to see. First, we will do x of t is given, and y of, so this is horizontal drive, let's say, and y naught of t will be a vertical drive. Now, just to give you a feel so that you can think about this just as an imagination of what is actually going to happen. This is the result is going to be, and again, we won't be able to go through the stability analysis. We won't be able to spend so much time on it. We will just get the equations of motion and leave it at that stage. The stability is a lot more involved in a sense. But the point is, if you have a horizontal drive, at least if you were to make this oscillatory, you cannot stabilize this. So if you do this, you cannot stabilize it. But if you were to do this vertically, there is a critical frequency with which you can oscillate. And if you go beyond that, it can actually stabilize. And you can actually, I mean, it's not very common. I don't see this videos of this in YouTube very much, but there are, it exists if you search the right way, and it should be differentiated that one is feedback based. Like one is you look at it, if not us, that you can make a sensor that gets feedback and then does that. But that's not what we're talking about. Here it is natural, like you do blindly, you just oscillate it higher than a certain frequency, it'll get upright. And couple of years back, or actually 3 years back, Dustin, a graduate student here, he was very hands-on, and I had at least a couple of equipments needed, and he took it and built a inverted. Pretty straightforward. You just had to put an oscillator there, and what he did was, so I had a speaker for this purpose with a strong diaphragm. And you connect use a program or just audio and connect one single frequency, like usually Mathematica can do this very easily. So it oscillates, and then you just have to connect this small rod. So that was a primary thing. And he did that, and it was done in a very nice way. And it is probably, he's still here. Dustin, are you familiar? So he's probably in his office or in his lab. You will see that it is still with him, so feel free to ask him to show you. And it's sort of interesting effects. This has the consequence of this shows up in various fields. In trapping, for example, if you're familiar with any kind of atomic traps, they all use this concept in one way or the other. So whenever you, I mean, what is common is what is called Paul trap. Actually, I can show a video, right? Yeah, so the idea is very similar. Yeah, since we have this videos here, how do you show this? I have to start. Yeah, I don't think, oh, I had to record it, right? Because Harsha might be looking at it. Okay.
You can screen share.
Yes, first start the Google, right? And then screen share. Yeah, let's, okay. So I think it is Paul trap, I think that's what it's called. In the more experimental sense. What is this? Why is it not going? Help. Ah, here we go. Yeah, this one, I think. Is this so slow or I'm not clicking or what?
Very slow.
Uploading 0%. Wow. What's happening? Okay, hopefully this works.
Okay, this is a specially made.
Oh, I had to stop
gravitational
this
potential.
and share it, right? Okay, share and everything,
Or you can just click on the,
or just click on this. Okay. Okay, so we're sharing this and
Okay, this is a specially made gravitational potential well in 2 dimensions that satisfies Laplace's equation, meaning that the curvature everywhere is 0. And as an example of that, here we have a curvature which is positive in this direction, but at every point, there's also a negative curvature which exactly balances. So the sum of the curvatures in 2 perpendicular directions is always 0 for every point on the surface. That's how the surface was constructed. And this is typical of any 1 over r squared force, such as gravity, electromagnetism, etc. That means if we have a confining potential well in this direction, we have an unstable potential well in this direction, and the ball cannot be stable confined. There's no equilibrium point that I can put the ball on and it will be stably confined in that space. Now, interestingly, there are a set of solutions if this saddle is rotated. And I have a rotating a motor here which will rotate the saddle. But it requires a very special frequency to be stable. So if I'm below the frequency, the ball gets thrown out. If I'm above the frequency, the ball gets thrown out right away. But if I adjust the frequency to exactly the right value, we can create a stable condition for the ball in the center.
okay. So that's a 2-dimensional generalization of what we consider as, oops, I need to stop this. Okay. Okay, hopefully the audio went on the other side. Yeah, but that's not really an inverted pendulum. That is actually a Paul trap. That is the idea how whenever in all the atomic physics, atomic and molecular physics lab, whenever you think of an atom being trapped, that is what is a classic example used. that is a very model, that's a gravitational trap if you want. A general, instead of gravity, if you put in a electric field, and instead of the mass, if you have a charge, then you use the same idea. So the trap is made by having an electric field in one direction, an electric field in the other direction, and you oscillate it. So oscillating electric field is the idea of rotating it, and if you do it the right way, you can actually make it work. So, but notice that's a dynamical trap in the sense that it is wanting to fall, but you catch it. Like if it's trying to fall that way, you catch it this way. By the time it falls on the other side, you keep catching it. And it's the same idea here also. This will try to fall, but now the potential energy typically is typically for potential energy is this way. So when it tries to fall, this is stable, right? That's a stable potential energy. Now, if it is this way, there's no way you would say that, oh, I cannot. That's not going to be stable. And that's the inverted pendulum. But now you're going to oscillate this. What you're saying by oscillation is that for a moment, you'll make it upward. So the potential energy oscillates between positive to negative. So it can go up for a moment and then come back. So it tries to fall. So the moment it tries to fall, you make it up so that it goes back to the center. And by the time it goes back to the center and comes back, for a moment you come down and go back. So it seems like it is down, but it is dynamic in that sense. Very, very hand-waveringly speaking, if you want. But let's see if you can try to get the equations of motion this way. And of course, you can write the equations of motion using Newton's equation itself. But let's use the Lagrangian way to do this in this context. And let's see how the equations of motion are different if you have a horizontal versus vertical, and if there is a connection, we can okay, so that's what it is. Notice this is the angle theta here. Typically, this would be the angle like you would have the pendulum this way, right? So it is slightly different in that context. Okay, so Lagrangian, we say there's only one mass, right? You would say is equal to half m x dot square plus y dot square. Let's assume this is happening in 2 dimensions. Third dimension, in general, will be having a third dimension also, but for simplicity, let's keep this as just simplicity for the analysis, if you want. And minus the potential energy would be minus of mg times y. So that's all. One should be careful here, so like all the time when we were doing Lagrangian, we always said this is dependent on L of x as a function of time, x dot as a function of time, and an explicit time. And in this case, this is driven in the sense that x naught is a function of time here. Right? So it is driven, and that's that explicit time dependence that shows up. So in that sense, you're pumping energy into the system. Right? Pendulum is unlike that. There is the potential energy available. You have that, but here the potential energy is the energy that we are supplying is not showing up in this. This is the energy due to gravity, right? So there's an external piece of energy, some external force that is coming up, which we are not accommodating for, and that means that energy will not be conserved. And how do we see that in the Lagrangian? That involves the idea of Hamiltonian, and we'll come back to that in a discussion very soon. First, we will do small angle, and then we will do the. We have not yet done the boundary. We always said that boundary points will not are stationary, right? So whenever we release that, we will have the idea of why this is energy and so on. Okay, so let's see how we can work this out. We ask what is our position x, correct? X of this mass, and we know that x as a function of time is equal to x naught as a function of time plus L, so L times, so what is this, L times sine theta. Theta is a function of time. If L is fixed, or I should say, what is L? So that's the L is the length of that rod. So origin is somewhere here. Let's say if this is vertical, like let's say this is your origin, so that's your 0, 0. And this is just a time t. This could be oscillating up and down. I don't care. So in general, x is wherever this point is hinge, and you add on to that. And x of t is controlled by whatever function I provide in here. And we will try to keep this as let's say. So let's say x naught of t could be an amplitude a, like a times cosine of omega naught times t. Right? I'm oscillating it with a certain frequency. And let's keep it sine actually, so that you start from 0. Sine omega. Like it's convenient to start from 0. If you want to, actually, let's not even call it A, let's call it capital X naught. And y naught t similarly is equal to y naught times sine omega naught t. Of course, these two need not be the same. And actually, yeah, should I do that? Yeah, in principle, these need not be the same, but let me keep it simple because I want to isolate this. Of course, one of the analysis could be that there is both of them are there, but I'm going to isolate it. Either I will keep this or that in the analysis, just for simplicity again. In principle, that would be bigger. Oh, there is a, we have to move this. Okay, so with that, we can write y of t also. That's y naught of t plus L cosine theta. The only difference is that there is a driving force in that. So x dot, so the velocity, if you want, yeah, we're not right. Yeah, velocity is equal to x dot, which is capital X naught. When I take a derivative, I get omega naught times capital X naught times cosine omega t plus L theta dot times cosine of theta. Right? And y dot is equal to, again, do the same, omega naught, y naught, cosine omega naught t plus, or is it minus? It's minus of L dot sine theta. And we need velocity, so this is square, right? So we'll square this and add x dot square plus y dot square. That's equal to, when you square these two quantities, yeah, it would have been good if I made this go in a circle, right? Should I change this now? No, that's not. Yeah, let's not tweak this. Okay. So this is omega naught square x naught square cosine square omega naught t plus, so that is maybe we should put it like this. Since this is common, x naught square plus y naught square times cosine square omega naught t, right? That's the square of these two quantities coming together. When I square cosine square and sine square, that will give me a 1. So that's just this. And when I do the combined quantity in there, so let me write that separately. So that's plus omega naught. And they don't combine, I suppose, correct? They don't combine because there's an x naught and y naught. So this is omega naught, 2 omega naught, x naught L theta dot times cosine right, I think so. Minus of 2 omega naught y naught times L theta dot cosine omega naught t and sine theta. Correct. And of course, y we already have is equal to this. So now that these two information, we can actually write down our Lagrangian. So Lagrangian would be equal to half m of this quantity. Remember that the kinetic term is just basically theta dot square, right? That's the primary term, but there is this theta dot showing up, so we have to be careful. So this is half m, the whole of this v square. So let me collect them. So this is theta dot square. So it's the first term that shows up. What is the quantities that has theta in them? So it's plus whatever has theta in it. So let me write that as up here. So it's 2 omega naught L theta dot, 2 omega naught L theta dot, and the rest of, and I can write cosine omega t. So common. And I have x naught times cosine theta plus y naught times or minus y naught times sine theta. And there is a mass half of that, so that's n. Right. So L distance and theta dot square. I think that's correct. So I've taken care of these two, and this acts, since there is no dependence in theta dot, that doesn't come to the momentum expression. But let me write that down. That is the input of energy, if you want. So it's half on this square. So half m omega naught square times x naught square plus y naught square times cosine square omega naught t, and we will subtract the energy, that's mg times y, which is y naught, which is mg y naught sine omega naught t, and that is a minus mg L cosine theta. Is that clear? That's your complete kinetic energy, if you want. We can, if we were doing small angle approximation, you can do it at this stage itself, but just remember that whenever we make small angle approximation at the Lagrangian level, you have to keep a higher order because you'll be taking the derivative, but we'll come to that later. As of now, let's just keep the whole expression and let's define our momentum, right? So this is dl by d theta dot. That's our momentum with respect to generalized momentum or canonical momentum. Any questions at this stage?
Did you actually repeat exactly what you said? I'm sorry.
Oh, I said just now or before?
About that term, you said something about a canonical moment.
Oh, yeah. So so this is our Lagrangian, and I'm going to differentiate this with the angle theta dot. So, or before that, I think the idea is that first recognize what are the values it depends on. It depends on angle theta. That's the only coordinate, right? So only parameter that decides the motion is angle theta, and then there is theta dot, and there is time. So if I find the partial derivative of the Lagrangian with theta dot, this will be called the generalized momentum. Right? So this will be the generalized momentum or canonical momentum. Or canonical momentum. Remember, in general, it is mass times velocity, right? That's what we say is momentum. If it was a standard problem, that's what we will get in rectangular coordinates. But in other coordinates, you don't get the standard verb. And since there is energy being pumped into the system, it won't even be mass times velocity. There will be more terms showing up because there's this term. Right? So it doesn't have to be mass times velocity. So what is generalized momentum? Just take that derivative, right? So this is m L squared times theta dot. And dimensionally, what is that equal to? ml squared theta dot will remind you of angular momentum, right? So this is not a linear momentum because we are working with angular coordinates, that's angular momentum, but it is not purely angular momentum because there is energy being pumped in. Angular momentum is not conserved, so how does it show up? That's dependent on this partial derivative. So let's see what this is equal to. That's the second term also has that, so that's plus m omega naught L cosine omega naught t times x naught cosine theta minus y naught sine theta. So again, coming to the interpretation, I think Ken, you said interpretation wise, what is this contributing from? If there was no driving source at all, then this is what will contribute. And that's typically the angular momentum that gets conserved. This is the contribution to the angular momentum because of the driving force in the x direction. This is the contribution to the angular momentum because of the driving force in the y direction. And of course, the angular momentum will not be conserved. If there was no driving force, then you expect that it will be conserved. Probably no, because gravity is there, right? That will not be conserved. But the change in angular momentum is your torque or force, generalized force. So this is the way the momentum is, angular momentum itself is changing. That's good, but we also have the generalized force, if you want, and that's just defined in terms of the Lagrangian as with respect to theta. Instead of theta dot, you take the derivative with theta, and again you look at where is the contribution coming from, and you look at the places, and there is this term here. There is no contribution from theta here, and there is a contribution in there. But that doesn't mean that this won't get any role to play at all. There is time derivative in here, and when you take the time derivative, that can get a contribution. Okay, so partial derivative of L with theta is equal to m omega naught L dot cosine omega naught t, and that's equal to minus x naught sine theta minus y naught cosine theta. And where else does theta show up? And that's down here, the potential energy from gravity, right? So that's plus mg L sine theta. This should be slightly looked at carefully, because if the pendulum was in the downward direction, that's a typical pendulum, then this shows up with a negative sign, right? Because it is it's an attractive force, right? It attracts force. But here it is repulsive. So the tendency is for it to go away. The force makes you go away. So that's the plus sign showing up if I was to differentiate. And these are the forces, the torques actually. This is actually a torque, right? Similarly, this is a torque due to the driving force in the x direction. This is a torque due to the driving force in the y direction. So that's an interpretation if you want. This is the change contribution to the momentum, and this is the actual torques that is contributing to you because of the drive that is existing.
You see the torque?
Torque, yeah. Because this is with respect to the angle, this is the torque, but typically it is not easy to interpret that like that. Because we are familiar with angular motion, we say this is really the torque, but otherwise it's a generalized torque. Sorry, generalized force. A generalized force with respect to the angle theta. So this is the generalized momentum, this is the generalized force. Okay, that's the interpretation. Now, what is your equation of motion? We take the time derivative. But seems like it's a huge equation, but let's see. So this is time derivative of the momentum, generalized momentum. That's equal to m L square theta double dot. Now notice, don't forget the time derivative. There is a time derivative here, and of course there is all time derivatives everywhere else, but it's also the forcing quantity. That's the contribution. So that's minus. First, let me do the theta contribution from thetas, and then so first let me go to the theta. So that's it will give me a theta dot. So that's plus m omega naught L dot minus x naught sine theta minus y naught cosine theta. That's with me. And we have one more term now, because I can differentiate with respect to time here also, and that gives me minus m omega naught square times L times sine omega naught t times x naught cosine theta minus y naught sine theta. Sweet. So in principle, what's your equation of motion? You equate these two, and that's your equation of motion. But let's try to simplify this if there is any simplification. Usually there is a small amount of simplification at this stage. I'm going to equate these two now, right? That's our Euler-Lagrange equation. So this is, so Euler-Lagrange equation is m squared theta double dot plus let me pull all this out if you want. Yeah, so let me pull all this because I think this two cancel, right? So this is plus m omega naught L theta dot cosine omega naught t minus x naught sine theta minus y naught cosine theta, and put this also in there. So at this stage, I'm going to bring m. Yeah, I'll do this in the next step. Let me do one thing at a time. Omega square L sine omega naught t x naught cosine theta minus y naught sine theta. And that whole thing has to be equal to the generalized force, which is equal to m omega naught L theta dot cosine omega naught t minus x naught sine theta minus y naught cosine theta, and plus mg L sine theta. I just wrote it down these two lines, equated the two, that is all that I did. But one thing is immediate, there is a cancellation there, and that's this term completely cancels out. These two terms completely cancel out. That's a significant amount of simplification in there, and if I use that, then my equation of motion become m L square theta double dot, right, minus. Now at this stage, let me write this in the right form. So m, I want to write this as m L, and let me write this as let me write this as ml omega naught square times x dot times sine omega t times ml and there's cosine theta. So I recognize this, what this is, right? And that is, of course, ml squared, dimensionally correct. Again, another term, which is plus ml omega naught squared y naught sine omega naught t sine theta is equal to mg L sine theta. That clear? So let's go back and interpret these two square brackets. Remember that x naught of t was equal to capital X naught times sine omega naught t, like whatever that driving force is. So what is x dotted with? T, so that will be omega naught x naught cosine omega naught t. That's like the velocity, angular velocity, not angular velocity of these oscillations, and acceleration x naught double dot t is actually equal to minus omega naught square x naught sine omega naught t. Let's call this the acceleration of this drive, right? So let's call this ax of t. Is that clear? That's an acceleration, right? Position, first take the derivative, and second derivative will be the acceleration associated with the drive. Same thing here, there's y naught of t is equal to x naught sine omega naught t, correct? And this will be y naught of t is equal to omega naught x naught of cosine omega naught t. And this will be a y of t is equal to y naught double dot of t is equal to minus omega naught square y naught times sine omega naught t. And at this stage, actually, even though I said these are oscillations, you have given up. I mean, you can go back and give me any acceleration you want, and it is only the acceleration that contributes. Like it could be any function. It doesn't have to be sine or cosine, because all that would have gone through anyway, and it would have again cancelled out. So it didn't matter that actually it was actually sine and cosine. So everything would have been very general. It was just that that actually led us to that. But now you realize, oh, this is much more general. So what is our equations of motion in that case, in the general scenario? ml square theta double dot minus ml. Now this is x naught, so that's ax t as a function of t times cosine theta plus ml, and again acceleration in the y direction now, but this time with oh, I should be switching the sign. I'm sorry, because there is a of t has a minus sign, so this should be plus and this should be minus. Sorry for that. Because there's a minus sign here, I want to absorb that minus sign. So that's sine of t is equal to mg L sine theta. Notice the special feature here that so this is the important interpretation that is going to come in, that one comes with sine theta and one comes with cosine theta. Sine theta is coming with gravity. This has a role to play. Mg is acting like gravity. So first of all, mass cancels out, but we can keep it as it is. So this is ml square theta double dot is equal to, let me move it to the right, and I have mg, so not g, so let me say m l times g plus ay of t times sine theta, and of course there is this another term which is minus ml x of t times cosine theta. Okay, so should be careful if I'm So that's your equation of motion. And let me do one more thing in here. And I'm not canceling this m purposefully so that I can see the how these are the forces, right? If not for Ay and At, this is just simply the gravitational force that is coming in. So now make the small angle approximation so that this is much more clear. It is not necessary though. So this is small angle approximation. So small angle approximation is theta being small compared to 1, which is 1 radian. That's 57 degrees. And that involves sine of theta being equated to approximately angle theta itself. If you're making the small angle approximation at the level of force, we just have to keep it to order theta. If you're doing it at the energy level, because we'll be differentiating to get the force, we have to keep it to order theta square. Right? So that's a general thing. We will see that again. But cosine theta, due to that reason, can be replaced by 1. If it was in the energy, we want to keep this 1 minus theta square over 2. Because a differentiation will actually give you the angle theta. So if it is energy, you want to keep it to a higher order. Again, it is not that it will make any mistake, it's just that it is correct only to the 0th order, then you don't get the physics of it.
So if you were to go back to our
Mhm.
Lagrangian and then do the small angle approximation, that's when you would have the 1 minus theta squared.
Exactly. Good. Yeah. Because when you take the derivative there, then you get the one theta showing up. Good, very good. Yeah. Good observation. Okay, so what are these equations in that presence then? ml square theta double dot is equal to ml g plus ay of t times angle theta. And minus ml axt. And now interpret this. Notice the x drive is not very, it's just separately sitting there. It just acts like a force, right, in the horizontal direction. But here, this is sort of changing the role of gravity. Just at a very naive level, how would you have stability if this was a negative sign? This is attractive, right? This is stable. Can it be negative? Yes, if ay is larger than g, this can be stable. Right? At least for a momentary time, this is more, this can be negative compared to this. Right? Remember ay, so this is what you're saying is that this is time, g is positive, that's 9.8 here, and ay could be oscillatory, and you could have this motion, right? And every time it crosses that, effectively g is negative, which means it will oppose the angle theta. Right? So the moment this becomes negative, for at least for that duration, the force is in the opposite direction of theta. And that's what makes it so in this case, it tries to go that way. And the moment it crosses it, it tries to go the other way. So if you have sufficient balancing power here that it doesn't actually throw it off, then you can actually pull it back and you keep oscillating this. And that's that feature that shows up. So in the y direction, it is possible to oscillate. In the x direction, it's not. But that's it's not completely clear that, oh, is it really going to stabilize this? That's a little more work. Stability requires a lot more analysis there. And it can be shown that, so if you, again, this is not, or I can say, with a much more concrete explanation, one can show that G, AY has to be greater than, magnitude of AY has to be greater than or equal to G for that stability, at least that is needed. And if you notice magnitude of that, that's nothing but omega naught square times x naught has to be greater than or equal to G. Right, that's what the condition is. So if your frequency, so it depends on how much is the amplitude of your drive, right? How much is this amplitude, x naught. So if the amplitude is large enough, or the frequency is large enough, either way you can get this. You don't want the amplitude to be too large because then you're having a ruler. That's too much. That really disturbs the system too much. It's like you take the person and oscillate it. That's not really interesting because that you expect if you actually take the person and carry it around and oscillate the whole pendulum significantly. That's not very surprising, but you keep this low, but you change the frequency very high. So you are having this hand, the amplitude is very low, but you do it really fast. Right? If it is really fast, and then it will balance, and that's non-trivial. You don't expect that to happen, and that's very non-trivial and has interesting effects.
So that's why not right there?
Oh, that's why not, yes, thank you. That's why not. Thank you. So that's a nice feature that shows up. But again, it does not lead to oscillation in the y direction because there is like, here the idea is that it switches gravity. And what one can do is for example, interesting plants, right? You can ask if you have a plant, how does it know when to go up and when to root goes down and the stem goes up, right? And so the typical understanding is that there is one of the cells at the tip of the root and tip of the stem, they are sensitive to gravity. So basically they suppose we imagine one cell to be like this. There's some object here which goes down or up, right? Whether it is in this direction. So they have a sense for gravity. Like that's okay, that's good enough. But now the question you can raise is that what if you oscillate it, right? Like if you keep this oscillation, will it get confused with the direction of gravity? As simple as that. And there are lots of interesting questions you can ask in this context. And I will actually stop. Like I have about 7 minutes, but I think this hopefully does a reasonable job of explaining how the Lagrangian is. Of course, you can do many problems on this. Expectation is that you do, but I will switch over to a small angle approximation, and then next time try to introduce Hamiltonian and talk about the symmetry consideration, about the boundary. How does the boundary come into the picture? That's all. Any questions, comments?
Oh,
Yeah.
So you didn't take the Lagrangian with respect to x or x dot.
Yeah, because that's not dynamical. You see, this is, you mean this, right?
Yes.
Because this is not associated with the mass. Right? First of all, we are not heating
I see.
and we are actually driving this.
I see.
This is not, I mean, you usually say it is not dynamical. You're actually controlling this.
I see.
So it's not dynamical is that you let it go and let gravity decide where it will go.
Understood.
Right? Or else you have a force, you should let it have some freedom. Here you don't have any freedom, right? What is this going to do? It's going to do exactly what you're going to do. So it's not dynamical in that sense.
So I guess anything with like angular t, the angular velocity times t, anything with that is probably
Yes,
going to be
yeah, no,
because it's drive.
Exactly.
Okay.
And it does happen that all those derivatives cancel out. One thinks that no, this is actually contributing. It shows up here, it goes here, but actually they all cancel out. Like even though there is a driving feature in there, they all cancel out, and this piece doesn't even show up anywhere. Right? That is, remember, Lagrangian is not unique, right? I can add up any function of these kind of quantities and it doesn't matter. Right? So that's your overall function that's independent of that. It pretty much acts like a constant. So only few things contribute. Good observation. Thank you.
Oh,
Yeah.
No quiz today.